A. Alright, so yesterday I was introducing to you parallel vectors. Okay, and we said that vectors are considered parallel, okay, so long as they are scalar multiples of each other. Right, so this is on your page 15 of your notes. Okay, so it need not be of the same direction. Okay, so opposite direction can also be parallel vectors. Okay, so therefore we can say that for parallel vectors, they will be scalar multiples. Okay, so if I have a vector A, okay, and a vector B, they will be A equals to KB, whereby K is a number itself. Okay, any number will do, or a fraction, decimal, or whole numbers will be fine. Negative numbers will also work. Okay, so we can then conclude that it's a parallel vector. Okay, then after that, yesterday I also introduced to you that if I were to have A and a scalar multiple of A to be expressed in this manner, okay, the magnitude of Ka itself is equals to the modulus of K times the magnitude of A. Okay, I just want to emphasize that the modulus of K, alright, what this means is that, okay, so let's say if I have a modulus, okay, this is what we call modulus. Modulus of number 3 itself will always generate for you a positive number. Okay, so the value of modulus 3 will be 3. Okay, while if I have a negative 3, modulus of negative 3, like I mentioned, the modulus function is always to generate for you a positive number. So therefore, it will still be 3 itself. Okay, so be it positive or negative, the answer, the value of it, okay, of the modulus of it will always be a positive number. So that's the idea and the concept behind modulus. Okay, just a very, very fundamental one. Okay, for us to actually refer us back to example 14. Okay. So looking at example 14, okay, we want to figure out which of the following pairs of vectors are actually parallel. So we know that if the vectors are actually not equals to 0, so long as they are scalar multiples, okay, they are going to be parallel. So looking at part A, since I have 6, 8 and 2, 4, okay, we notice that for 2, 4, okay, if I want to translate into 6, 8, okay, so maybe I just compare the 2 and the 6. Let's look at times 3, okay, so if I were to times 3 to 2, 4 itself, what I will get is that 3 times 2 I will get my 6, 3 times 4 I will get a 12. Okay, so we see that although the top number, the x component is equal, the y component is not equal. So therefore, we say that 2, 4, okay, cannot become a scalar multiple of 6, 8. Neither can 6, 8 become a scalar multiple of 2, 4. Alright, so if you were to choose a multiplication of 3, no matter what, whatever number you choose, it will never give you a 6, 8. Okay, so we will say that say 6, 8 is not a scalar multiple of 2, 4, then the vectors are not parallel. Okay. Okay. Next, for part B, I am comparing the vectors negative 8, 16 and 24, negative 48. Okay. So I typically, okay, always look at the x component. So negative 8 and 24, we think about what is the number that I have to multiply to negative 8 such that I can get 24. So 8 times 4, 8 times, forget. 8 times 6, right? Hang on, no. Mental sound breakdown, sorry. 8 times 3, sorry. 8 times 3 will give you a 24. So 8 times negative 8 times negative 3 will give you a 24. Right? So negative 3 times negative 8 and 16. X component will give us a 24. 4. 3 times 16, that's 48. So we get a negative 48 here. Okay, so we see that, okay, our negative 8, 16, once multiplied by negative 3, I can get a 24 from negative 48. So therefore, they are scalar multiples of each other. So we say that since they are actually scalar multiples of each other, the vectors are considered parallel. Okay. Next, we look at part C. Okay, we have 30, negative 6 and 20, negative 4. Okay, so if I were to look at the x component, we think about what is a number that I can multiply by 20 to give me 30. In this case, it's not going to be a straightforward integer. Okay, it's going to be a fraction. Right? So we know that for 20 and negative 4, if I were to divide by 2, 20 divided by 2, I'm going to get 10. Okay? And then I will have 30, right? Okay, so I will times 3. So 3 over 2 times 20, or you could use your calculator to figure it out for you. Okay? So 20 times 3 over 2, you're going to get 30. We apply 3 over 2 times negative 4, and I'm going to get a negative 6. So we observe that the two vectors are actually scalar multiples of each other, and hence they are going to be parallel. Okay, so example 14, we address how to actually prove or show that two vectors are actually parallel. So in example 15, we are actually informed that these two vectors are actually parallel. So if they are going to be parallel, they must be scalar multiples of each other. Okay, so in order to be from 4, negative 3 to arrive at a 12p, we're looking at 4 times 3 to get a 12. Okay, so that will help us in finding out the value of p. So 3 times of 4 negative 3 should give us a 12p because they are parallel. Okay, so 3 times negative 3 is equals to p, and p will have to be equals to negative 9. Okay. For example 16 and 17, okay, we do our simplification in terms of finding the single column vector, similar to how we work our matrices. Okay, so in part I, we're trying to find the column vector that represents u plus 3v. So that will be u is 1, 2. V is negative 2, 1. So this is what it means. Calculate it and we get negative 5, 5. you just also very quickly do part 2 to figure out what is the column vector representative of 3u minus 2v minus w. Okay, I see some of you already doing parts. Question example 17. Okay. We should get 4, 8 as our answer. Okay, for example 16. Alright, before I move into example 17, okay, earlier just now asked a good question. I thought that it's important for me to address as well. So maybe just rewind a bit to example 14. Okay. So just now when doing our part B, okay, so our part B, when we were trying to figure out whether this is going to be a scalar multiple of 24, negative 48 or not, we realized that we can times 3, right? Okay, so we can say that 3 of negative 8, 16 is equals to 24, negative 48. Okay, so this is one way of writing it. Another way that we can think about is to see whether this vector, is it a scalar multiple of this or not. Okay, so we can say that 1/3 of 24 negative 48, because 24 if I were to divide by 3, negative 3, right? Sorry, yeah. Okay, so 24 if I were to divide by negative 3, I'm going to get my negative 8. And negative 48, if I were to divide by negative 3, I'm going to get a positive 16. So this is another way that you can write it, whereby the scalar itself need not always be an integer. Okay. I also want to emphasize that when you want to talk about division, okay, so when I did the calculation of 24 divided by 3, okay, we never ever write in matrices or in vectors a column vector like this, okay, divide by 3. Negative 3 in this case. We never ever write it in this manner. Okay, this does not make mathematical sense. Okay, we do not define it, right? When it comes to vectors or even in matrices. Okay, so you catch it. Okay, please sit up straight. Right, so if you want to talk about division, we always multiply by a fractional number. So in this case, it is your negative 1/3. Okay, so I hope that you are all clear about that as well. Right, and don't go into doing the division. Okay, so then going back to example 17. Oops. Okay. Given A and B and also 2A plus B is equals to 5, 3, we want to find the value of x and y. So same thing as your matrices. Okay, 2A plus B will be 2xy. Plus b is 2 negative 3 equals to 5, 3. Okay, you can simplify the vectors on the left to write it as 2x plus 2, 2y minus 3. And see that the x component will be equals to each other and the y component is equals to each other. So x is 1.5 and y is equals to 3. Okay? Okay, where we want to express a vector in terms of two other vectors. Could I erase this already? Okay, so if you're given in this case the vector AB and also given how P and Q is like, we want to express our AB in terms of P and Q, okay, without figuring out what is the column vector, okay. So in a diagram manner, okay, if I have A to B expressed like this, okay, let's say if starting at A, okay, and I want to have my vector P starting first. So if I have my vector P, that is 1 to the right, 2 upwards. So from here, 1 to the right, 2 upwards, I will get a single vector P to be moving from point A to here. But of course, this point here is not the end point that we want, which is B. And yet, if I were to put in, add on, continue with a vector Q, I'm going to end up moving here. Okay, and that might be a bit too far away from our objective. Okay, so maybe how about, okay, if we were to continue adding another vector P. Okay, so you notice that if I have a vector P plus vector P, so there's now 2 vectors of P. And then reaching B itself, it is just 3 units to the left, okay, from where I have just left off. And 3 units to the left is the reverse of my vector Q. So this direction will be negative Q. Okay, and therefore AB equals to 2P plus Q. Okay, what this is trying to tell us, alright, minus what? Oh, sorry, oh, okay, sorry, I thought I would minus it, sorry. The heat is getting into my brain. Okay, so 2P minus Q, okay? So what I'm trying to say over here is that whenever you have a vector AB, okay, there is actually a combination of some other vector. So in fact, you can also travel P some more lah. Okay, just that you will have to actually end up going back in the longer direction back to B. Okay, this might not be the only expression, okay, of combination of P and Q to result in AB. Okay, surely there could be more, right? Just that it will end up in bigger numbers. Okay, there can be multiples of this, right? So that's the conclusion that I'm trying to draw over here. Any vector can be uniquely expressed, okay, in terms of 2 other non-zero, non-parallel. Coplanar means that they are on the same plane, okay, meaning same dimension of the vector paper, okay. Vectors U and V. Sorry, this one should have O. Okay. So this idea we have actually addressed it earlier already when we look at simplification of some vectors. Okay. Next thing that's important, okay, is this idea of position vectors. Okay. The idea of position vectors is to draw some relation, okay, between our vectors to our coordinate system. Okay. So in this case, I have given you a grid, okay, with some coordinates, some x values and y values going on. Okay. So let's say if I were to consider the point 25. Okay. So just an example. Okay. So if I were to have a point 25, that refers to here. Okay. When it comes to position vector is always defined between the points that we have to the origin. Okay? Position vector will always be from the point to the origin. So, if I were to draw the line for the position vector, this is what we are referring to. So this is the position vector for OP, or for the point of P relative to O. Okay, and we describe it as OP. Right? And that will be 2 units to the right, which is our X component, and then 5 units upwards, which is our Y component. Okay? Next, if I were to let Q to be 5, 3 as an example, so 5, 3 will be here. Okay? So that means that our position vector of Q to O, the column vector that represents this OQ would be 5 units to the right, 3 units to the top. So we observe, okay, that for position vectors, it is exactly the same as your coordinates, just that it is written in a different format, that's all. So even if I have, let's say, a vector, let's say maybe here, okay, R. If I want to write down the position vector OR, okay, so O to R, so therefore the arrow is in this direction. R has the coordinates of -3, -2. The position vector will be -3, -2 as well, because it is after all from O, 3 units to the left, 2 units downwards. Okay, so there is some consistency between our coordinate system with position vectors. Okay, so now that we have found out the position vectors for OP and OQ, and if I want to express, okay, a column vector that represents the vector PQ, okay, making use of my idea of OP and OQ, so P to Q is as good as traveling from P to O to Q. Okay, so it's just back to our addition of vectors. So PO plus OQ, which is your negative OP plus OQ. Sorry, let me zoom in. And OP is your 2, 5, so negative 2, 5 plus OQ is 5, 3. We find that it is 3, -2. Okay. Obviously, without doing this calculation, we can also derive this column vector 3, -2 if we are given the diagram itself, since we know that the X component from P to Q will be 3 units to the right, and then the Y component is 2 units down, so it's -2. Okay, so with a diagram, we can clearly know that it's 3, -2. If without the diagram, we will then have to do such a calculation. Okay. Okay, next thing I want to introduce to you is a term. Okay, so we can regard PQ as the movement from P to Q, and we call this a translation from P to Q. Okay, in language-wise, when we say we translate something, would be probably from your mother tongue. Okay, translate it into English, alright. But if you're looking at the movement from P to Q, they're like kind of translating, meaning to change, okay, from P over to Q. So PQ itself is what we call a translation vector, okay, that describes the movement from P to Q. So this movement that we're referring to is P to Q. Okay. example 19. Okay, we want to write down the position vectors for the point P and Q, and then express PQ as a column vector. Okay, so I mentioned already coordinate system and your vector system is the same. So could you figure out the answer to part A? Okay, give you about 2 minutes. Right, figure out the answer to part A before we talk about part B. Done with part A. Okay, what's the column vector for OP? Okay, what's the column vector for OP? What's the position vector of P? 8 and -2. And then for the position vector of Q, what would it be, Noi? -1 and 7. Okay, to figure out the column vector for PQ, we can say PQ as PO plus OQ. PO is negative OP. So that will be negative of 8, -2 plus -1, 7. And we have -9 and 9. Okay, any questions? Right? I want to focus on part B now. Okay, whereby it says that there is a point A, 6, -7, being translated by the translation vector AB, -4, 5. And then we want to find out what is the coordinates of B. Okay, so what we interpret of this statement is that AB is this, and the position vector A of A, which is written as OA, will be 6, -7. Okay, so if I could find out what is OB, the vector OB, that will tell us what is the coordinates of B already. Okay, so to figure out the coordinates of OB, or rather the vector of OB, that is OA plus AB. So we will have 6, -7 plus -4, 5. And therefore B itself is 2, -2. Okay. Questions? Next, we take a look at example 20. We want to find out the magnitude of AB. Then after that, part B, we want to find out the coordinates of B. which can be similarly done as what we did in part D over here. And then it's given that CD is parallel to BA, and CD is given as that. We want to find the value of K. Okay, so I want you to spend next 5 minutes, right, to do example 14. Let me set my timer. you could at least do question part A and part B. Get it? To find out the magnitude of the vector AB, we take square root of negative 3 square plus 4 square. Okay, and that will give you 5. Okay, and then for part B, 5 units. And then after that, to figure out the coordinates of B, we first figure out the position vector of B, which is OA plus AB. And we have negative 1 and 9. Okay, so coordinates of B, answer the question. Okay, in the coordinate form, so negative 1, 9. Alright, part C, right? Okay, I noticed that some of the presentation seems a bit all over the place. Let's try to neaten up our presentation. Okay, so it says that CD is parallel to BA. So since CD being parallel to BA, it will mean that CD must be a scalar multiple of BA itself. Right? So question gave us that CD is K 13.6. M is a scalar number that I anyhow introduced. Okay, so you can choose M, you want to choose A, B, C, any letter also can, as long as it's not K. So M, then BA will be the negative of AB. Which essentially is a 3, negative 4. Okay, so this is where CD being parallel to BA means, it means that it is a scalar multiple of each other. So what we can do is figure out what is the value of M. Okay, and that can be done by 13.6 is equals to M times of negative 4. So M is 13.6 divided by negative 4. That will be 3.4. After figuring out M by making use of the Y component, okay, we can then find out what is K, which is M times 3, and that will be 3.4 times 3. And, sorry, what's that? And it should be 10.2. Yeah. Hang on. Negative 3.4, no wonder. Okay, thank you. So you should get negative 10.2. Okay. Next we look at question 21. Okay. 21 should be manageable for you. So, will you also spend 5 minutes to work on question 21? Before we head into the main focus of this entire chapter, which is all the questions at the back. Are we done with example 21? Okay, shall we check our answers? Alright, let's take a look at our answer part A. We should all get our coordinates to be 5, negative 3. So OR has been given to you to be OP minus OQ. OP will be 3, 1. OQ is negative 2, 4. So coordinates of R is 5, negative 3. Okay. Likewise, when it comes to part B, OS B equals to OP plus 2OQ. OS is XY. OP is 3, 1. OQ is negative 2, 4. So to simplify this, we get negative 1, 9. So X is negative 1 and Y is equals to 9. Okay. So let's look at example 22. Okay, so all the questions that we have been doing prior to example 22, right, okay, are all building towards example 22 onwards, okay, this kind of questions, right? So I erase that, okay. Okay, so in example 22, right, we have OAB being a triangle, D is a point of BA, such that BD is equals to 2 over 7 BA. So very often you will be seeing a lot of expressions like this or even like this. Okay, and we need to understand it carefully, right? But before we jump into that, okay, OA is given to be as a vector A, right? And then OB is given as a vector B. So they did not give you any numbers, alright, in terms of a column vector to represent these vectors here. We want to find out what is AD in terms of A and B. So AD is a vector moving from A here to D. Okay, so if you want to highlight it, which is here. Okay, so how are we going to figure out, okay, the column vector of AD when there is no grid, nothing, so you can't really draw. Okay, so and then also, okay, even if you want to think of AD as moving from AO to OD, that is going to be a challenge as well, because you do not know what is the vector OD at all. Okay, and that will actually be something you may need to go and find out in extra steps. Okay, alternatively, of course, you could also consider AD as a movement from A to O to B and back to D again. Nonetheless, we still need to figure out what is the vector BD going to be. Okay, so in order for us to find out what is the vector of AD, what we can do is to make use of this concept here. Okay, it says that BD is 2 over 7 of BA. That means that, okay, BD is 2 units while BA is 7 units. Okay, you could also rewrite to think of it in ratio form, where you divide BA over, where you see BD over BA equals to 2 over 7. So in ratio, okay, this is what it means. So BD is 2 units, BA 7 units. Okay, we can find out the vector of AB. Okay, if I can find out the vector of AB, figuring out the vector for part of it, which is AD, wouldn't be a problem, because it will just be a fraction out of the entire AB vector. Okay, so because after all, they're all going to be parallel, right? So AD will no doubt be parallel to AB. Okay, so it will be a scalar multiple. So we first find out what is the vector of AB. That will be done so by considering AO plus OB. And AO is negative A, OB is B. Okay? Since we notice that BD is 2 units while BA is 7 units, that will tell us that DA must be 5 units. Okay, so that total 7 units, right? Okay, so AD is 5 units out of a total of 7 of your A to B. You must make sure the direction remains the same. We're looking at A to D. It must be A to B. So equals to 5/7 AB. And AB we have already found it. So we have 5/7 times negative A plus B. You could leave it in this manner, or you want to expand it, that is fine as well. Similar challenge. Although we are not given where is this point E, but we are told, okay, in a descriptive manner, that E is a point on the line OA, such that 5 times of OE is equals to 2 times of EA. This might be difficult to actually imagine and figure out. Okay, what you could do is to express it into a fraction or ratio form like this. That might help you in visualizing where point E is. Okay, being able to visualize, okay, is very helpful when solving vectors question. So in this case, 5 times of OE equals to 2 times of EA. If I were to shift things around, OE over EA, divided by EA, OB equals to 2 over 5. So the ratio of OE to EA is in the ratio of 2 is to 5. So 2 units for OE, 5 units for EA in the entire line of OA. So 2 units, 5 units. Okay, so there is that kind of idea of proportion over here. So you're not looking at being exact. So E could be somewhere here. So that we can see a ratio of 2 is to 5. Okay, when it comes to vectors, right, when we arrive at this topic itself, counting units, being able to understand ratio would be very helpful. Okay, so now moving to the main part of the question is asking whether ED is parallel to OB or not. So to figure whether ED is parallel to OB, okay, in order for it to be parallel, ED must be a scalar vector of OB. OB is just B itself. So we want to see whether ED, ED itself over here, could it actually be expressed as a scalar multiple of B or not? Okay, so let's go and find out what is the vector of ED. There are a few ways that you could go and look for the vector ED. Okay, few paths that you could take. So ED can be found by either traveling from E to A to D, or you can do E to O to B to D. Okay, longer path does not always mean that it's wrong, alright? But shorter path does help a bit, since finding EA could be done, okay? And also AD has already been found in part A. So ED is EA plus AD. EA itself is 5 units out of total 7 units of OA. EA is this direction, OA is in the same direction, so it is 5 out of 7 of the vector A. Okay, plus AD being our negative 5/7A plus 5/7B. And that would leave us that this minus this becomes 0. We are left with 5/7B. And ED is a scalar multiple of OB. So we conclude that since ED equals to 5 over 7 OB. Then ED is parallel to OB. Questions? Yep. Why is it? Where are you looking at? This one. Why is it B minus A and not? Why is it negative A plus B? So nothing, no issue? Okay. Okay, so homework. Exercise 5C, question 12, 16 and 17. Please have it submitted by next Wednesday, alright? Okay? So next Wednesday, that is your 21st of March.